All right, welcome to lecture 21. We have assignment 8 deadline on next Monday, and assignment 9 will be ready soon. So deadline is just after the reading week. So after today's lecture, I won't see you for more than 1 week. And so if you have questions about all the material, feel free to send me an email. And we have exercise classes this week, and I really encourage you to go. So this week it will be about why what is this? Sorry. This week it will be about the density of state. So this is about the density of states, and you are asked to pay attention on different ways to get the same thing, and then also to pay attention on what determines the density of states. These two are kind of important for the remaining 3 lectures. So let me say this again. We are going to do it a little bit differently, a little bit more aligned with the solid state physics treatment. That's because we are about to talk about metal very soon. Okay, so you will see you will get the traveling wave solution for the particle in the box. Okay, I talked about this on Monday's, sorry, today's Wednesday. Yes, on Monday's lecture. Okay, so go back and look at that. Another thing you should pay attention to is about the dispersion relation. Right now we assume the particle, the kinetic energy is related to the K by this. What if we have some other dispersion relation? So I didn't use the term, but this is really called the dispersion relation, how the energy depends on the momentum. And I can, of course, come up with different types of dispersion. For example, what if I have linear dispersion? What happens to the density of states? So this will be answered tomorrow in the exercise class. So please pay attention on these features. Where can you get things like this? For example, for the second one, you can get a situation like this when you talk about phonons, a lattice wave. So this will be, even if I don't have much time to talk about this in this course, they will be useful for your solid state physics, for example. And of course, if you have photons, you will have some kind of this linear dispersion relation, right? The energy is like what you have in the energy of photons, right? You have E equals PC, right, over there. So that is how you define the slope of this. So for the photons in the free space, this is how you write it, right? So if you know the energy and the momentum, you get the speed of light here as a slope when you plot E versus P. So what we have here is the equivalent of situation in when we want to apply, when we want to describe solid. And even for some situation, you can have the lower case. For electrons, there is a class of materials which is rather new, and we call it the Dirac material. So there, the electrons dispersion relation, when you do the band structure calculation, you can really identify region like this. You get an energy which is dispersing linearly in K. Okay, so please pay attention on this when you attend the exercise classes or exercise class. I don't think you will be so keen to go to 2. Okay, so last lecture, this is some summary I wrote for you. This is what we covered last time. So last time we developed an important concept of this bundle. We want to use this idea to describe our gas, right, indistinguishable particles, and we obtain the partition function. Now you can look it up, and you will see the partition function. And here I write you the form, which is the continuum expression. So this is wait a minute and give me this is expression equation is 10, equation 1038 in my notes. Okay, so we develop really, you can recognize the trace of it, right? But the partition function is, if we do the discrete form with sum over G sub K, and then we have e to the minus epsilon sub K divided by KBT. And we develop it that way. And then I also told you we would like to use the continuum form because there's powerful, we can do a lot of calculations. Okay, and we got to this point, and we realized last lecture, we realized that actually what we have been doing, the derivation of the density of states for particle in a box, is really equivalent to treating a problem of an ideal gas. And this ideal gas is a monatomic ideal gas because we only have the translational kinetic energy included in our Hamiltonian. I didn't solve the Hamiltonian, but I told you this is the answer. Right? You learn it in other courses. And with this recognition, and the next thing to do is to really plug in the value of density of states, right? So here we really take this 10.38 and we plug in G of epsilon, right? So we plug in this G of epsilon, which we derived earlier, and then we will try to see whether we can identify some results based some familiar results from our past knowledge of an ideal gas. Okay, so once we do it this way, we get to this point. Okay, I want to talk about this equation a little bit too. So here we identify. Now I ask you, what is the dimensions of this partition function, and you told me it's dimensionless. So we can naturally identify some kind of quantity which takes the meaning of concentration. And this n sub q is the quantum concentration. And the point is, if we have n, which is much smaller than n sub q, we can use classical statistics. Okay, which is something we derived. And the opposite limit, when you have your concentration, which is much larger than n sub q, you have to use quantum statistics. And from here, I want to really immediately draw your attention to this. How do you play with this case, right? So for example, you remember the estimation I did about this 7 million people sharing 35 cars? If you are observant, you will realize what I did there. Really, I plug in the thermal energy, I plug in the mass of helium, I use helium. So all these quantities are really entering this quantum concentration, right? So that calculation is equivalent to this viewpoint here. I could have define this quantum concentration. If I knew this quantity, I could have done it that way. I could have calculated quantum concentration, and then I could have calculated the concentration of my helium gas in this volume, which I kind of did something not quite the same, but the deep down the meaning is quite the philosophy is actually equivalent. Okay, so now there I kind of say we are at room temperature. Now you can begin to see how I can begin to mess up the situation. So there, when I did the calculation, I told you we have very dilute system, so we are naturally in the top case. So suppose you take that system and begin to cool down. What you are doing here is really modify n sub q, right? Because you cool down, and now originally you have this concentration of your problem to be much smaller than quantum concentration, and I can use the temperature as a trick to lower this n sub q, and eventually this condition will break down. Then I will enter the case when I have to do proper quantum statistics. And this is coming up soon. This is coming up so soon that probably just before or after the break today, you are going to see quantum statistics. Okay, so another thing we did was we plug this in, right? We plug this in, and then we get the we plug in G of epsilon, and we get this partition function, and that allows us to go back to our sausage machine again to see whether we can turn some good function of states out, and we found that we got the internal energy, which is as expected. So this is 3/2 N kBT. Okay, we found this very nice. We expected this, as I say here. This is our expected, our recognition of the problem. We suddenly realize what we are doing is really a monatomic ideal gas. Let's try to get some try to prove it. So we got this. That is the first thing. And second, we also managed to get the equation of state. How do we do this? We use the Helmholtz function. We use our thermodynamic knowledge, and we get our NKBT divided by V. Okay, so we get all this. And one thing that I wanted to do but didn't manage to do is the entropy. That is the next thing I want to do today. Okay, so just to remind you about the problem, this is also from last slide. So this is also from last lecture. It's a slide from the last lecture, and I told you entropy. If you look at the entropy, and if you are not careful, this is when you begin to see problems. What are the problems? This is the thing, right? This is the relationship between the system partition function or assembly partition function and the single particle partition function. I told you this n factorial is necessary, and you will have to include that. Okay, so and now we also have we have this, and this can be a bit messy. Look at this. We have this term, and why don't we plug it into here, right? If we plug it into here, and we will see what happens. Okay, so let's try that. So that is the next one. You get a famous equation. This is called the Sacru-Tetrode equation. Okay, if you plug it in, now actually is the steps are here. You really, I already did it once, and if I summarize it here, I know this is gonna happen. Never mind. Okay, start again. So this is Sacru-Tetrode equation. This is Sacru-Tetrode equation. Okay, now I ask you probably last week or even a little bit earlier, I told you to remember one equation, right? If you only want to remember one equation, this is the one you should remember. Okay, and then you can then try to look at the problem differently, right? So now, what do you know? And this is what I asked you to remember. And this is what you know. You know this single particle partition function, which we spent time to work out. And this is this expression earlier. Here, this one here. This one. Okay. So this is maybe it's worth to write this down. This is this guy. KBT H square. Okay, so if you want to use this expression, you need to assume the relationship between them. Okay, so I will give you the result right away. So here is the result. I color coded for you. So S, entropy. If you do it with the correct boom, you get this result. You get log V 3/2 log T. You can begin to see why you get this, right? You get this log V 3/2 log T. And then you have a bunch of constant which you probably don't want to write out. That will be related to this 2 pi m kb. This is a bunch of constant. So I will just group them together. H bar square. Now, if you do it correctly, you have this term log n plus another number. Okay, so this is the correct one. Correct means you use this. N. Okay, the incorrect one, I will use a different color, right? So 2 cases. The incorrect one, you get this. You get this term, you get this term, you get this term, but you don't get this term. And then you get a different number. Okay, so you get this term, this whole thing. You can try. You can see this n is gone. And then here we go. Here, if you do this. Okay, now my question for you is this. So there are 2 expressions, 2 and 1. Tell me what's wrong with 2 in the chat. So expression 2 is wrong. I tell you it's wrong, but then I want you to tell me why this is wrong. Oh. Anyone? This one. Expression 2. I use different color. It's a very colorful slide. I want to know why this is wrong now. Of course, I told you the partition function is wrong, right? This one, I already long time ago, I already justified that we have to use the second one. Okay, so there I already told you I want something else. Okay, so I will begin to write the note and you continue to type. Okay, so 2 is wrong because for indistinguishable particle, I don't see so far I only see one correct answer. We can't use this. And it's a very, there's one correct answer already by no, I don't want to name. One student got it right. Now the incorrect expression, I want you to look at this and then try to recognize what's wrong. 2 is wrong. Okay, now I tell you the answer. Okay, if you look at 2, the problem here is it doesn't guarantee that S is extensive. That is the problem. That is the deep problem here. Otherwise, everything this year I don't get very active discussion. Last year I get a lot of answer, all kind of answer. Of course, it's only one correct answer I want, but then there are students who complain that this cannot be 3/2, it has to be 5/2. There are lots of very interesting discussion. This year I only get very little. But then the key is this. So one student got it right. We need to make sure S is extensive, right? So how do we do that? So you go ahead, you go to, now, the easiest one is to look at 1. Then you will know why 2 is wrong. So we want to go to the left-hand side and then find everything that scale with the system size and then just double it, for example. Okay, so for example, I go to the right-hand side, I know N has to double, right? So N has to go to 2N. Okay, and then what else? KB, of course, doesn't change. And then volume has to double. Right? Let's say I put 2 identical systems side by side. That is what this is an operation I do. T doesn't change, constant doesn't change, and N double. And you will see if I do this operation for 1, so 1 will correctly give me S is 2S. So S will go to 2S. Right? Because now that's the beauty of this guy here. This has to be here to guarantee this to happen. Right? So you double this. Right? You make it a log of 2V, and this one is minus log of 2N, and this is log. So you take the ratio, the factor of 2 disappear. So the entropy in the end will be twice of the original entropy, because this N, prefactor N in front, get double. Whereas here you have a problem. You cannot get this result for number 2. Okay, so this is the thing about this equation. And this actually appear in one of the final exams. And you can actually extract a lot more information from this equation. And that is part of the assignment. The next assignment, I will ask you to do this. So this is an exam question I reproduce as the assignment. And please read my assignment and follow the instruction. Okay, so this is the equation you can get, this famous equation. And if you still recall your midterm, this is kind of similar to midterm question 2. Midterm question 2, I also told you about this. I gave you some form of equation. There's actually another presentation of this Sacco-Tetrode equation. And I didn't do this statistical mechanics. I gave you things that then you can deal with. For example, I merge all this constant into something else. And then you get the key features of Sacco-Tetrode equation. And I already asked you about this question. Okay. Entropy has to be extensive, basically. All right. So that's it for this. Now, this is one more thing. So keep in mind what we are trying to do here. So what we are trying to do is to gain some satisfaction by testing our machinery against something we know, right? So we try to get the result that we know, we are familiar with. So that would be these two, right? Equation of state and the expression for the internal energy. This one is a little bit far. Unless you are an expert on thermodynamics, you probably won't recognize this right away. But then see this as a new result that you learned today. Okay, you acquire some new knowledge about ideal gas, and this is an equation to describe the ideal gas. And as I say, from here you can extract other things and see you can see your assignment. And what about now we are talking about a system which only has kinetic energy. We started by talking about particle in the box, right? We started quantum, if you like. Yes, we started right away like this. But then don't forget, we are also talking about a system which is dilute. So when it's dilute, we start with quantum, but in the end, we argue that we can enter the classical regime. And this should remind you of something you learned in the kinetic theory of gases. Okay, so can we, with our treatment, obtain the key result of the kinetic theory of gases? There's this Maxwell-Boltzmann distribution of speed, right? You remember this? I don't know, maybe last year in 2041, you learned about this. You get this distribution of speed, which is not very symmetric. It's a bit like a distorted bell shape that allows you to talk about the root mean square speed, means the average speed, and all this, right? Can we get this? So of course the answer is yes. Otherwise, I won't talk about that here. So how do we do this? I will sketch it for you, and then you can look at my notes. Okay. So I will write this. We know from our K bundle treatment, after we work out the equilibrium distribution, we have this expression, right? We have this n sub k, which is the number of particles in the K bundle, can be written like this. Okay, we saw this, right? This is the result we get. But this actually is kind of continuing from the past slide. We want to talk about kinetic theory of gases, and I would like to use a continuum form. So how do I make it into a continuum form? I will have A is A, and then you have G will become density of states. Okay, so this you just replace one by one, and then exponential factor becomes like this. You don't attach the subscript anymore. And once you do it this way, what is your NK? Your NK will become NE-DE. Okay, so this also becomes continuous. And if you have this DE on the right hand side, you have it on the left hand side, and that tells you the number of some kind of number within an interval D of E. Okay, so that might not be that difficult. You probably remember all this. One thing you may not remember, let's see whether I can get it here, is this. Right, so this you don't remember, fine, you derive it or you can look it up. Okay, and then you plug this in. So you have this whole thing in. Okay, let's be really lazy for once. Let's be really lazy for once. And well, okay, A. All right, so this is G of E, DE, and then just copy everything first. This is my expression 10.20 in the note. Okay, now the rest is not that difficult, but you need to realize one thing. You don't even have integration to do, so you just have to rearrange the thing. But then one thing you probably don't remember is this. How do you deal with this? Now this I have shown you that A is the prefactor, which is related to the Lagrange multiplier alpha. So this A can be written as n divided by the partition function. This is A. Okay, so actually here, this is here, the first line here. N is related to the single particle partition function like this. So A is n divided by Z. Okay. And that gives you a rather messy expression, but you need it because I'm trying to give you something that you can recognize. Right now, you might not recognize, but once you eliminate A, right? So this is, I just replaced it with the form of the single particle partition function. Now you can plug this in and simplify it, right? You can see a lot of simplification, right? You have this pi here, you have 2m to the 3/2, you have 2m to the 3/2, right? So here you can simplify. Okay, so just a few steps. Can simplify the right hand side, and I will write the end result. This will cost you maybe 1 minute or 2 minutes. Okay, and you have this square root of energy dependence, very famous one, and then you have this. Okay, at this point you might ask, so what? This is not the Maxwell-Boltzmann distribution of speed. This is not something I know. That is because you didn't make it into the form you know. How do you do that? You do it by changing the coordinate. You don't want energy, you want speed, right? So this is a distribution of energy. So you want to go to the speed domain. And what's the relationship between energy and speed? For this case, as I already said, the energy is purely kinetic. So this is the only thing you can do. Okay, so now that's it. You can change from n EDE to n speed d speed by changing the coordinate. Whenever you see epsilon, you just replace it by a half mv squared. And don't forget the dE, right? This is related to the question we have last time, right? So you have a half m 2v dv. Okay, whenever you also have to treat this and plug it in, tidy up, you will get the expression I have in the note. So this is a Maxwell-Boltzmann distribution. Okay, a distribution of speed. Let's write everything. Okay, so try it and you will get this expression. Actually, you are nearly there. We are nearly there. Right? Just do that, and don't just stop at the algebra. Pull up your plotting software and try to plot it and see whether you can really reproduce everything that you recognize before. Okay. All right. So that is the end of this chapter. Now we can begin a very short chapter, and this is the chapter 11. This is about quantum statistics. So again, let me copy down this again. NQ 2m pi kbt h squared. Okay, this part really is about how to exchange identical particles. So we are still talking about identical particles. Now we need to begin to worry about one situation. That is when the particles have the chance to compete for the same energy state. Okay, so that is when we need to begin to worry about what happens. Can they really go into the same box, or they have to occupy different box? Are they allowed to have the same set of quantum number? Okay, so there we will have the distinction between bosons and fermions. And that is the remaining of this course. We need to develop the statistics and use them. And I believe this is maybe with a bit of luck, this is something you are learning right now in quantum mechanics, or maybe a little bit earlier than me. So I don't want to spend too much time to talk about this. but I will just extract the key information that is useful for me. My intention is to focus on the statistics, and the rest you can look up your the notes from other courses, or actually my notes. I gave you something not as complete as quantum course, but it's enough for you to follow my presentation. So we want to really focus on the exchange of identical particles. Okay, this is a very tricky problem, but we can reduce it. We can start by looking at a simple case. What is a simple case? So the simple case will be like this. Let's begin by looking at two particles. That's my strategy. I will look at two particles. Then I will look at three particles. Then I look at n particles. So let's just increase the complexity a little bit, step by step, to see what happens. So suppose I have two identical particles described by a single particle wave function. So I will call this phi. I have to label this in order for me to keep track of them. Although they are not distinguishable, but for this discussion, I need to really know which one is which before I do the exchange. Then after the exchange, I will argue that if you look at the system, you cannot tell the difference between and after the exchange. Okay, so I will label it like this. I will do this phi 1, and another one naturally will be phi 2. So these are the two the single particle wave functions for two particles. One I call 1, the other one I call 2. And then this depends on a set of generalized coordinate. Okay, so just follow me. This depends on this guy. So R1 can be all kind of relevant coordinate. For example, the coordinate in space, the spin, etc. Anything you want, as long as it's relevant to the system. So technically, this in my note, I use the vector notation, but I don't want to do it here because it's messy. So just remember what I meant here. Okay. So technically, this is R1 bar, but I don't want to clutter my notation. All right, so I will have R2 for this. This can, for example, be the particle, the same type of particle, identical particle, but sitting at a different coordinate. And therefore, you will have the usual interpretation, right? So if I take this square, that tells you the probability of finding this particle. So this is related to the probability of finding the particle. Actually, finding the particle 1, because I take phi 1. Okay, and now this one will be later. Let's continue to treat this two particle system. Now, what is the combined wave function? If I treat particle 1 and particle 2 as one system, I can write down some sort of wave function for this particle. Okay, so this wave function will be I will call this the combined wave function. And this will have will depends, of course, on both R1 and R2. So I will have R1 and R2. Okay, and this wave function is the wave function for this combined particle. And now, what if I swap the coordinate of the two particles? Then I will get another wave function like this, right? I will get R2, R1. So this is interchanging the position, the generalized coordinate of the two particles. All right, and I look at the system and I come back and remind myself that I'm really talking about identical particle. Therefore, after I swap them, I cannot really tell the difference between them. So I can put the equality here. Can I convince you that this is the case? Do you buy this? Yes or no? Is it okay? I'm talking about two particles. I swap. Is this something you learned recently and you can accept this already right away? More? Yes. This is wrong. What I just say is wrong. You must not accept this because this is now this is a trick question. Sorry. So I want to trick you. I cannot write this. This is a criminal. I can only write this. All right. This is a very standard problem. If you really understand the interpretation of wave function in quantum mechanics, you will kill me not long ago, like 2 minutes ago. You would just shout and say this is not correct. Okay, so what I can do is this, and actually one student got it. Very nice. So what does it mean? That means this exchange is correct, right? Everything I say is correct, but what I wrote down was wrong. I cannot equate the wave function before and after the exchange. What I can only do is to equate the probability. Okay, I will have the same probability of finding them because it's an identical particle. I swap them. I cannot recognize the difference, and because of this, I have to introduce the phase. Or I can also say that if I insist on looking at the wave function itself, what is the relationship between them after I swap? Is that I have to introduce plus or minus 1, right? You take the square root, you have plus or minus 1. Okay, that is one way to look at this. And this plus or minus, it will give you the symmetric wave function or the anti-symmetric wave function. One will give you fermion, one will give you boson. Okay, and another way to look at this is this. Now I can also write it like this: the wave function itself. Maybe this is more complete for some of you. If you are very familiar with this, you will say, okay, I cannot equate this. After I swap, I will acquire a phase. This is my phase. Standard way to write the phase. Okay. All right. So what if I swap again? Let me swap again. So if I swap R1 and R2 again, I will acquire the same phase. Okay, and then I look at the left-hand side and the right-hand most line. I realize they are the same side of R1, R2, and here I also have that. So this can only be true if this product is 1. So that gives you the same result. So maybe this argument is better. Okay, but they are equivalent argument, depends on what you like. You swap and swap again, and this is what happens, and you must acquire the phase. Okay, so what is the relevance here? Let's begin by treating fermions. So copy. Okay, I want to keep this line here. So for fermion, okay, so for fermion, I want to exchange with minus sign. That is to say, I want the anti-symmetric solution. So how do I do this with two particles? And I write down the general form, and now I want to build this wave function. I want to build this wave function R1, R2 for fermion for two particles, and then I want to respect this property, anti-symmetric property. So I know I can do it this way. So I can take the wave function. If I just do it like this, I don't get anything. And I know there will be other solution. And this is my claim. This is a solution that works. Okay, so let's check. Now you can put the normalization. Let's do it. So here, each of them, if you swap, obviously because of the this minus sign here, you get the once you swap, you get the minus sign. Okay, so this is a correct way to do it. And how do you do the boson? So this is for fermion. So for boson, you just change this minus to plus. Then once you swap R1 and R2, you just come back to yourself. So that is the other solution. So this one will get the so for the fermion, we want this E, this phase vector to be -1. And then for boson is the other case. All right, so this is not bad, right? We are slowly building things. And now, what is the case of three particles? So the three particle, we will have three single particle wave functions. And we know this is one of the solution, one possibility. Okay, so I put phi1 at R1, and I put phi2 at R2, and I put phi3 at R3. Okay, indistinguishable. So there must be other ways to put that, just like here, right? I can put phi1, the first particle at R2 and the second particle at R1, right? And now how do I deal with this? So you should note that this is only one possibility. And there is actually a systematic way to write down all this, and this is called a Slater determinant. This is Slater determinant. It's a determinant, so you need to write a matrix. You can for this small system, it's not that difficult to write all of them, right? Now, for if you have two particles, it's easy. You only have two terms. If you have three particles, you can think about it yourself. You can list out all possibilities, and you have three factorial terms. Okay, so those are the possibilities you can have when you have three particles, and then you exchange two of them at any time. Okay, so what is this? For example, you can try to be systematic. How do you be systematic? The systematic way to write down everything is like this. First, I keep the particle 3 unchanged. This one will be sitting there all the time. And then I swap the other two. So if I swap the other two, that is equivalent to the line, 2 lines above, right? So I only look at 1 and 2 and swap them. 1 and 2 and swap them. So let me swap. And for fermion, this is what happened. R2, phi2, R1. Okay, and then you expand this, you get two terms. And you repeat for the other two, and then you will be able to find 6 unique terms, and all the and in total you will have 3 factorial terms. Okay, now these can be elegantly actually I don't want this is a way for you to gain intuition. The Slater determinant really is a way to give you the complete wave function for fermions, and that will be for the 3 particle case, it will be like this: R2, R3. And then I would just immediately write this down. This is the total number of possibilities. Sorry, 3 factorial is the total number of possibilities. This is factorial entered it here. And then you have a determinant of a matrix. So this is a determinant of the matrix. Let's bring this up like this. Okay, so if you have three, you can convince yourself that if I write the matrix this way and you work out the determinant, you will get if you expand this matrix, the determinant, you will find all the terms you need. So I have 1, 2, 3, and then I have 1, 1, 1, and then I have R2, R3, 1, 2, 3, 2, 2, 3, 1, 2, 3. Okay. The only way to convince yourself is to really go and expand this. Now you can also see if I stop at 2, right? If I only have 2 by 2 matrix at the top, and this becomes 2 factorial, you can see I really reproduce the line above, just at the top of your screen. Okay, and the 3 particle case is completely represented by this matrix, and therefore I can go all the way to n. Okay, so if I go all the way to n, I will have the determinant, the selected determinant for n fermion. So this is R1, this is n Rn, and this is phi 1 Rn. Okay, and this of course will becomes 1 over square root of n factorial, and this one I don't want to write. This will go all the way to Rn. Okay, so things in green color is only for 3 particles. This is really kind of good. I already told you how to build this. Now, suppose you didn't know how to build this matrix, right? I told you how to do it from 2 particle, 3 particle to n particle. And suppose you don't know how to build this, what information can you get from here? Look at this determinant. It really has all the ingredient we need to discuss the physics of fermion. If you exchange 2 particles, so if you exchange, originally particle 1 is described by phi 1 and R1, and you want to exchange with some other 5, sub 5 and R5, what do you do really? What operation when it comes to the matrix? Right, if you exchange them, what you do is actually interchange 2 rows, right? So originally you will have phi 1 and R1, right? And then now you want to exchange them such that now you originally you have this phi 1 and R1, phi 2 and R2, phi 3 and R3, etc. And now I exchange the coordinate to describe the particle exchange. So if I exchange R1 and R5, for example, and that is essentially interchange 2 rows. And that if I do that for matrix theory, you know, exchange, I will acquire a -1. So this is the same as the phase, right? So now just if you look at the expression earlier, if I exchange any 2 coordinates, before I only exchange R1 and R2, R1 and R2, and now I take R1 and R5 and so I swap them. And what happens then is I will acquire a minus sign like before for the case of 2 particles. Okay, that's one thing. That is important, but not directly impacting us. What is impacting us is the next statement. So if I let two particles occupying the same state, two particles, two fermion, occupying the same state. What do I do in this case? For example, I will let one particle two. I want these two to occupy the same. So this is what I demand. And once I do that, I will have two identical columns. Right. So if I have this 2 and 3 becomes the same, let's say 5, 3, then these are two identical columns. So again, from matrix theory, you know, this is 0. The matrix will be 0. So two identical. This will lead to two identical columns. And the wave function goes to 0. So this is not what we want. We do not like to see this. So how do we prevent this? The way to prevent this is to go to the source and demand this operation being illegal. So that leads to the Pauli exclusion principle. Pauli exclusion principle. Okay, now this is what we want. So when we do the statistics, what we really care is really this last statement. We have to be careful to put the particle carefully such that we respect this Pauli exclusion principle. Okay, and now just very quickly, how do you deal with boson? To deal with boson, you this is a little bit awkward. You expand your slater determinant like usual. You really just expand them like usual, and then you have to respect the sign, right? You know, when you do the determinant, now you do this, and then you get this list. Whenever you see a minus sign, you replace it by a plus, and when you see a plus, you keep it as plus, and that will give you the symmetric solution. So you can exchange any particle, no problem. You get plus. Okay, and that is that is the way you do this. Okay, so for example, I already say if you do the plus, that is okay. And there, now if you look at the two particles, this is kind of obvious. If you have 1 and 2 become the same, then the wave this phi will go to 0, right? If I demand the two particles occupying the same state, then 1 and 2 are the same. Phi 1 and phi 2 are the same, and R1, R2 can be different, doesn't matter. And phi 1 is the same as phi 2, and here I have phi 1 is the same as phi 2, then they subtract and become 0. What about boson? Boson, I already say, whenever you see a minus, you change it to plus. And if you have two particles occupying the same state, you have phi 1, phi 1, phi 1, phi 1. They don't go to 0. There's no way, no mechanism to kill them, to kill the total wave function. And therefore that is allowed. So for fermion, you can for boson, you have the luxury to put as many Bose particle in the same energy state as you like. Okay, so that is the key, and we just need these two lines, these two statements to build the statistic next, and that will allow us to discuss the Fermi-Dirac and Bose-Einstein. Okay, let's take a break. Come back at 1:40, and we will begin to give these two new equilibrium distribution. Okay, see you soon. Okay, welcome back. All right, next is the statistics. So this is Fermi-Dirac versus Bose-Einstein. Okay, so there are two different statistics. So Fermi-Dirac to discuss fermions, and then Bose-Einstein for boson. So remember how we treat the dilute case. I want to go all the way back to there. So when we had this K bundle, this is my the bundle. This is a K bundle, and we have we picked some average energy epsilon K, which we argue that this would be the good description for everybody in the bundle. And how many states in the bundle? We have GK of them. Okay, GK states. And we have how many particles? We have NK particles that we need to look after. So we have NK particles. All right, so let's begin. We are going to let's start from boson, because this is the easiest. We have NK boson. So let's again identical flow. We will look at this K bundle. We ask, how do you put these NK bosons in this GK state? So I have NK bosons, GK states. GK energy states, how do I describe them? I just use the partitions. I use the wall to describe all these energy states. I show you how to do that. Okay, so if I have a GK energy, let's say this is how many? 1, 2, 3, 4, 5. Now 4 partition is enough for me to uniquely define 5 different boxes. I can use them to describe 5 different energy states. Okay, and then I will draw it again. I would describe my particle by dots, right? So I will my boson will be can enter any of the 5 states. For example, it can go here, can go here, can go it can skip one and then come here, and then the remaining one can come here. Okay, so this is allowed because they are boson, they can share, and even if they really like each other, they can even come together, no problem. All 5 of them here, and then empty, 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 fine. Okay, this is also allowed. Okay, so how do I write down the number of possibility for the Kth bundle? And this is actually the same. Actually, this is identical to what we did before. Okay, you look at how many in total, how many objects you want to sort, you want to arrange. Then you have NK plus GK minus 1, right? You have 5 dots and 4 lines, so you do this. So how many different ways can I arrange 5 dots and 4 lines along the line, along the 1D dimension? Along one dimension. So I have this many different possibility, but I have to divide by the possibility of this NK factorial. That is because I cannot tell the difference between the particles, and I also cannot tell the difference between the partitions, so I need to do it this way. This is a coin problem. Okay, and at this point you realize, hey, this is identical formula. What is new? So what is new is the following. For boson, you cannot, you basically pretty much have to stop here. You cannot assume anything about the number of particles relative to the number of energy states. You don't know the relative size between NK and GK. So you cannot make that dilute limit approximation. The only thing you can do is to make a big number approximation. That is to say, you don't care about this -1. Okay, so this is what you can do. NK factorial, GK factorial. That's it. You cannot go beyond this. Okay, so let's copy this. I will need it soon. Okay, and what about fermion? So this is boson. how do you do fermion? Now, if you haven't seen my note, this is actually a very good exercise. Now, maybe I give you a little bit of time to think about this. Now I have NK fermions. I still have GK energy states. Okay, so how do I distribute this? What is this omega K? Anyone want to type? You can try this. Right, so this is the starting point, right? Once you get this right, the rest is just again turning on all this machinery of Lagrange multiplier, which you have seen twice, 3 times. We're going to see the 4th and the 5th time. You get your equilibrium function, distribution function. So the only subtle thing, it's not so subtle. The only key is here. How do you get this right? All right. So this is again counting. It's like a coin problem, head and tail, but you look at it differently. Okay, I will tell you how to do this. Now you have fermion, so you need to let me draw some box. This is my energy state again. I just turn it by 90 degrees. I turn this picture up here by 90 degrees. Okay, so I have this scenario. These are my energy states. I have GK of them. And this can either have one fermion or no fermion. Okay, understand? Right? This is what we did by analyzing the exchange property of the identical particles. We can either have 1 or 0. Okay, that is the way you need to know. Okay, you just look at it a bit differently. So you have now you can, if you can only have 2 possibilities, so you can call the one with a particle head, right? The one without the particle tail. Okay, so how many of them do you have? So your head plus tail will be the total number of boxes you have, right? The total number of energy states. So you have GK energy state. This is the total, just like the one in the top. I have that many boxes. Okay, the total number of coin, right? So what are the character of the box? There will be some with 1 particle, some without any particle. So those with 1 particle, I add them up, will be NK. So I cannot tell the difference between them, so I have to divide this out. This is NK factorial. And how many of them will be empty? The ones that are empty will be the difference between this. I have that many boxes, and NK of them are occupied by particle. So this difference tell me the number of empty boxes. That's it. This is my solution. Okay. All right. Right now, I see some answer about pairing them up. No, there's I don't know where this comes from. Maybe you are talking about the spin degeneracy. I don't know why you type about this. But right now, we just assume we don't care about the spin. If we want to care about the spin, we will just label them a little bit differently. For example, we can just artificially call this energy level 1 with spin up, 2 with spin down. Sorry, 1 energy, 1 up, 1 down, 2 up, 2 down, and we make them different. This is something that is easy to deal with later. So right now we just assume they are different boxes. I don't know how to label them, but they are different. Okay, so when you consider spin, I think that is why you gave me this answer. Okay, so that's it. This is the way to again. That's why we spend time to do this coin problem at the beginning. We use it so many times. It's a good investment. Okay, now let's move on. Standard thing again. So let's do it quickly. To get the both understand statistics, it's an equilibrium distribution. Okay, so I want to maybe use the wording to remind you that we are talking about equilibrium distribution. That's why we maximize the log of some omega distribution. We need to maximize log of this omega, which is related to the omega of the case bundle by this expression. This is the question I asked you last time. It comes back again. So half of you say sum, half of you say product. Now the answer is product. I hope you spend time to think about this. Why this is product. But very quickly, just in case you didn't invest this time, we can have now the way to arrange the particle in the case bundle is independent from the way to arrange the particle in, let's say, k+1 bundle. So these are independent events. So it doesn't matter how I do the case bundle, k+1 bundle doesn't really care, doesn't even know about this. And therefore, for independent event, we have to take the product. Okay, you can again convince yourself always by taking a limiting case of small system, which you can play this kind of trick. And this is my recommendation for doing the thinking process. All right, so come back to here. Then I take the log of this. This is the quantity I want to maximize. So I take the log of product of this guy up here. So this give me the sum. Okay, sum of what? Sum of log of nk plus gk, nk plus gk factorial minus log of nk factorial minus log of gk factorial. Okay, I'm going to do this once only. You will do the Fermi-Dirac yourself in the assignment. The steps are completely parallel. Okay, and I do the Stirling. So I will have a sum of k. I cannot do anything. Then I have nk plus gk, nk plus gk log nk plus gk. Okay, I will have minus this thing here, but I can have cancellation. Okay, I write everything down. Okay, I have minus nk plus gk. Then I do the Stirling for the other term. That will give me a nk log nk minus nk. So minus, there's a minus sign here, so it becomes plus. Okay, I write it a little bit differently. And then the next term, I have gk log gk minus gk, and there's a minus, so this becomes plus gk. So the point is you get this cancellation here. So this is what you can cancel. Okay. Okay, so what is the end result? The end result is I'm left with this log, something log, and then the other two log terms. And now I take the differential. Not too happy about this. It's the same thing anyway. So I do the differential d log of omega. So d log of omega will give me a sum over k. Now I do d log with respect to the change of n sub k, right? We want to find how how we can come up with the equilibrium distribution of the particle, right? So how many particle in the K bundle, right? Sorry, D. So just remember what are the constant, what are the variables. Okay, so this one I will have a product rule again. So I have NK plus GK, and log of this will give me another cancellation, another nice cancellation. And then plus now DK I already pull it out, and plus I will have a log of NK plus GK, and then I differentiate this, I get 1. And likewise, I have this NK, log of NK, differentiate, I get 1 over NK. And then I have the log of NK. And then GK, once I do the differential with respect to N, this is 0. Okay. And I have this nice cancellation here again. So this is the sum of log of NK plus GK divided by NK. Okay, this thing. All right, next standard thing comes again. We will do the Lagrange multiplier. We want this D log plus alpha dn minus beta du. This has to be 0. Again, these are chosen to be compatible with the node, and more importantly, to be compatible with some limiting cases I want to extract later. Okay, I mean the sign of the Lagrange multiplier. So these will give me sum. The first term is sum over dnk. Everybody will have dnk. So let's do a big square bracket for this. So I have first term is this. Second term is really sum of dnk. So I have alpha. And the third term, the term with beta, I will have to multiply by epsilon k. And this whole thing has to be 0. And therefore, in the spirit of Lagrange multiplier, don't say anything too much. You just extract this. And this has to be 0. Everything in the square bracket has to be 0. So I have this result. Okay, then I have this 1 plus GK divided by NK is e to the minus alpha. I will write 1 plus GK divided by NK. And that will give me exponential of minus alpha. Okay, let's group them together, plus beta. Okay, and I want to have reserve some space. Okay, so it's called the distribution function is commonly written like this. So I have NK divided by GK. That's what I like to have, right? For the Boltzmann distribution, you also have something like this. You want NK, you want an expression for NK. So you have NK, there you have NK is A times GK, G sub K times the Boltzmann factor. So I want to do something similar. So I want NK at the top. So this is what I have. E to the minus alpha plus beta epsilon K minus 1. Okay, so this is the Bose-Einstein. This is very significant. This result is very important. Okay, next. Copy. Let's copy. And we need this. Actually, we just need this. Okay, now suppose you do the same thing for the fermion. You take the other omega, right? The one for fermion, and repeat the same trick. If you have done a good job and really keep track of everything, the steps are identical, you do things correctly, you will get this result. So for fermion, what you will get is, let me make it more symmetric here. So for fermion, you get Nk divided by Gk is 1 e to the minus alpha plus beta plus 1. So this is the key difference. So this is the Fermi-Dirac. Okay, and beta takes the usual meaning. That is 1 over kb t. But alpha is a bit harder to now I will tell you what is alpha. Alpha is mu divided by kbt, where mu is the chemical potential. So mu is the chemical potential. Now this you have to trust me. The reason is this: with the current ensemble we use, it's not really easy to discuss the meaning of mu. Even to get alpha, even to relate alpha to mu is not that easy. You can kind of see why this is that you can have intuition, but if you want to really derive it this way, you need to go back, you need to do the ensemble theory properly. Now, this is not surprising because if you use your thermodynamic knowledge, you realize I didn't introduce mu for the first 6 chapters. And to introduce mu, I need to start a new chapter, chapter 7, which I call the non-standard beyond the simple PV system. That's to say, I need to really analyze a situation where I allow particle exchange. And that's how I did it in thermodynamics. So here is something similar with this ensemble. It's not that straightforward to treat this to get the expression for mu. But I can give you some intuition. This chemical potential is related to the number. And I always tell you this, right? When we do Lagrange multiplier, alpha goes with number, beta goes with energy. It's a bit like a song that you can sing by now, right? Alpha goes with number, beta goes with energy. So alpha is related to the number, it controls the number. And we know chemical potential plays this role. And therefore, you should also keep something in mind. If I have a system that I do not conserve the particle number, that's to say, so if I go back here, if I do not conserve the particle number, okay, where is it? I know. Okay, I will rearrange it later. When I do the Lagrange multiplier, you see I have this d of log plus alpha dn minus or plus beta du, and that has to be 0. If I do not conserve the particle number, I do not even need this term to begin with. So I will set alpha to go to 0, and therefore my mu will be 0. Okay, that should remind you another midterm question about photons. So if you I give you the thermodynamic treatment. If you do things properly, you will find mu to be 0 for that case, because for that system you do not conserve the particle number. You can create photons. You imagine you have a cavity, and that is the problem I set for you, and you can create photons, and therefore mu has to be 0, and that shows up here. Okay, And then there are a few things we can look at. So this mu is related to alpha. And then the other thing is, how do you make sense of this expression here? Of course, you can just say, I derived this, so it has to be correct. But you can also put a little bit more insight. What are the insights? For example, here, look at the Fermi-Dirac. So I will draw my energy level. Now, suppose I have GK energy states. What do I have here? If I have GK energy states, I can either have one particle, one fermion, or no fermion. Okay, so in the case that I have fermion everywhere, then my NK is identical to GK, right? I have GK energy states, and at most I can put one fermion in each energy state. So the limiting case will be I have NK equals GK. And most likely the situation will be I will have less, because some energy states will be zero, will have zero particle. So I will have this constraint for the fermion case. So for fermion, I will have NK to be less than or equal to GK. Okay, that is to say, NK divided by GK has to be less than or equal to 1. And that explains this plus 1 here. Okay, and if you look at this whole thing has to be smaller than 1. And this exponential factor will always give you something larger than 1. So this whole thing will be give you something smaller than 1. Understand? Okay, so this is one way to really now you need to be very careful about these two number here. Plus 1 and minus 1, it tells you a completely different world. So if you want some ways to remember, this is one way. Okay. And what else I can say? What else now I can also use this to talk about the classical limit. So maybe I will write a little bit down here. So you want this circle? I can put it back for you. So this discussion here. Now, classical limit. What is the classical limit? The classical limit, when we derived the classical limit, we didn't really say anything about fermion or boson. It's not because we don't have fermion or boson. It's just there's no need to talk about them. So now, if you don't have need to talk about them, that's to say in the classical limit, if I take boson or I take electron, as long as they are in the dilute limit, they will give me the same distribution, right? So I hope you get this point. If I take the boson, if I describe boson in the dilute limit, I don't really care about the character of boson. Likewise, if I magically change all boson into fermion, just by some magic, and otherwise everything is the same, I don't really need to pay attention on the character of fermion. And they are both going to give me the Boltzmann distribution. And how do I see this? I can also look at this mathematically. If I look at these two expressions for Bose-Einstein and Fermi-Dirac and try to reconcile, I would say, okay, in this case, I want to make them the same. How do I make them the same? The way I make them the same is to ignore this plus and minus 1. Then they will be the same. Okay, indeed, that will give you the Maxwell, the Boltzmann distribution. So let's try. So in the classical limit, the wording has to be very carefully written. I'm not saying that there's no difference between boson and fermion. I say no need. We don't need to differentiate them. fermion and boson. And therefore, I will come back and look at this expression and say, okay, I can make them the same if I ignore +1 and the -1. So I will just ignore. I will set them to 0. So there will be a 1 over this minus. Okay, and then this is indeed A times E to the minus beta. This is your Boltzmann distribution. Okay, but you might not like this argument. This argument is completely acceptable to me. I would just say this is 1 over exponential term plus lambda, where lambda is, when lambda is -1, I get BE. When lambda is 0, I get Boltzmann. When lambda is 1, I get Fermi-Dirac. But if you don't like this argument, then another argument is also possible. I will present that to you. Now, in the classical limit, what do we know? What we know is this: the number of particles is much smaller than the number of energy states. So I will have this, right? And be careful. This is not the same as this. If you think they are the same, you need to fix your eyesight. They are different. This is a dilute limit. Dilute limit. And how do I get dilute limit? I come back here. How do I make this whole thing very small? To make this very small, I need to make the denominator very large. So if this is very large, it means it's much bigger than 1. So I don't really care about 1. If it's 1 million plus 1 and 1 million minus 1, I don't care about this 1. So I can ignore the 1 and I will get the same result here. So this is another argument that maybe some of you find it more acceptable. Okay, so now this is done. Actually, we finished chapter 11. This is a short chapter about this Fermi-Dirac. So the next thing is chapter 12. Now I would like to start by a little bit of motivation, then I will let you go, because you will have a long vacation, not very long, 1 week. So it's good to think about the problem. So the chapter 12 is about Fermi gas, and that is the best example of using the Fermi-Dirac statistic. This is an occasion for you to practice. So the best example, sorry, I think I say too fast. So the best example of the Fermi gas turned out to be the electrons in metals. Okay, so this is part of the assignment problem, so I won't say too much. But how do you know electrons in metals really requires us to use Fermi-Dirac statistics? You know how you calculate the concentration and you calculate the quantum concentration and you compare them, and you will find that even at room temperature 300 K, so we will need Fermi-Dirac even at room temperature. This is very drastic, right? For you, when we talk about helium gas at room temperature, we know we can use classical statistics, but for electron, this is not the case. Okay, so this is a homework problem and you should look at this. And you are also encouraged to think about another type of conductor. If you take a semiconductor and repeat the same exercise, you will find that you can survive. You can just survive with classical statistics. If I give you a lump of material and ask you, is it metal or a semiconductor, you probably won't be able to tell me. But deep down, they are described by different statistics at room temperature. Okay, so we need to talk about electrons in metal, and we need to use quantum statistics. So a bit of history here. Now, this is a good place to talk about this. Now, electrons was discovered by J.J. Thomson. So in this year, 1897, so discovered by J.J. And 3 years after that, Paul Drude, this is the name, D-R-U-D-E, Drude, was very brave. He decided to describe this newly discovered particles, electrons discovered by JJ. He decided to just apply kinetic theory of gases, use KE theory of gases. It's just like what we did. Okay, we developed this kinetic theory of gases, and he decided to describe this collection of electrons using this theory. And he immediately encountered some failure. And what is the failure? And this is a failure that I hope you can already give me the answer. You don't need to tell me now. Okay, he failed dramatically to explain why the heat capacity of electrons is so small. What is the heat capacity we expected? So the Drude model is essentially kinetic theory of gases. So you know from today's lecture at the very beginning, I already tell you this is like ideal gas of electron. So there you should be able to work out the internal energy. You know the internal energy will be 3/2 NkBT. And if you take derivative, that will give you heat capacity. So this is a heat capacity that we expected but mysteriously missing. So this is the amount of heat capacity that had never been predicted. Now to benchmark it for you, if I talk about molar, you know how to do this. If I want to look at 1 mole, I will let N to be Na times Kb. And the heat capacity due to electron in metal is this much. How do you know whether this is big or small? It's very simple. You benchmark it to your Dulong-Petit result. So Dulong-Petit law tells you I will have a molar heat capacity which is approaching 3R. Right? This is when we talk about diamond, I mentioned this. Now, if you have the resolution to detect 3R, don't tell me you don't have the resolution to detect half of this amount. This 3R divided by 2. Therefore, this is a result which has been well known for a long time. The failure of which led Einstein to develop the Einstein model. And here, the failure of detecting this much heat capacity motivates something else. And that is the motivation of the need to use quantum mechanics to discuss the problem. That is to say, we need to use a proper statistic. The picture itself is correct. We have 3 electrons. They are not interacting. That is fine, but the statistic is wrong. Here, to get this, you need you basically implicitly use the Boltzmann statistic. But the correct statistic has to be Fermi-Dirac. So we need Fermi-Dirac statistic to analyze the problem. Okay, now I'm done, nearly done. So I want to give you one more distribution function. So this is a very special distribution I want to present to you. And this is the distribution of the midterm score. So we have 57 points in total. So this is one student get full mark. So this is 57 here. And one student gain 56. And the mean is this much, 36 points. And we have 32 students. So this is the distribution. Okay, so you can have a look. The idea is not really to compare with others, but you need to do better than yourself always. So if you identify something that you need to work harder, this reading week is the good chance to do it. And the solution will be discussed in some form, maybe in one of the exercise classes. Okay, so this is and from Friday, it will be the graded answer book will be released on Blackboard. So give us some time. We have to do it one by one. Okay, thank you. That's the end of today's lecture. Enjoy your reading week and see you 10 days later.